Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. And if you have been watching this video series from beginning, you will note that we are in a section called Derivatives of Polynomials and Exponential Functions. And all we've done so far is focus on polynomials. We've discussed what the theory behind the derivatives of polynomials are. We've discussed how to compute derivatives of polynomials. We've gone through tangent and normal lines for polynomial functions. And in the last video, we did some stuff that was a little bit beyond the basics for polynomial derivatives. And now we're in this final video. And this final video is actually for the final part of that title of this section, which is derivatives of polynomials and exponential functions. We don't actually take the derivative of all exponential functions here. We're only going to focus on the natural based exponential function e to the x. And it is such a beautiful based function, e to the x, and super powerful in the sciences. Very important. And so there are a few definitions for this number e. It is a limit, and I think we discussed that in a previous video, that e is defined to be a very specific limit. I think it's 1, the limit as x goes to infinity of 1 plus 1 over x to the x power. But here's yet another definition for this base e. So the base b such that the limit as h goes to 0 of b to the h minus 1 over h is equal to 1. So the only base in the world that allows you to run that limit and that limit becomes 1. There's only one base that will do that. And it turns out we're going to call that base e. That is, the limit as h approaches 0 of e to the h minus 1 over h is equal to 1. And it turns out that e is actually 2.71828 and so on and so forth. It is the e that we know and love. It's the only exponential base that satisfies this limit. Now, you may not recognize it, but I'm just going to say it now. This limit is the derivative of e to the x at 0. You might not recognize it, but let's go ahead and just showcase that. By definition, if we just allow f of x to equal e to the x, then the derivative will be defined to be limit as h goes to 0 of e to the x plus h minus e to the x all over h. But this will imply that if instead of looking at f prime of x, we want to look at f prime at 0, we would be looking at the limit as h approaches 0 of e to the 0 plus h minus e to the 0th all over h. And this can be easily rewritten, whoops, it's not infinity, that's 0, as e to the h minus 1, because e to the 0th is 1, over h. And turns out that e is the only base whose limit as h goes to 0 for that exact piece is 1. So this is going to be, by definition, e is the one base that does this. And so that is defined to be 1. And thus we know that f prime at 0, terrible handwriting here, f prime at 0 is equal to 1 for f of x equals e to the x. It's the exponential function. Let me just draw this in. Here's the exponential function right here. And it's the only such exponential function whose slope at time 0 for its tangent line is 1. All the other exponential bases have different slopes other than 1, at x equals 0, that is. Now here comes everybody's favorite theorem in calculus. The derivative of e to the x is actually just itself, e to the x. So for a while now, I've been saying the derivative is like you have this parent and the derivative is the child. This is one of those cases where the parent and the child are exactly the same. It's like cloning in a way. So it's the derivative of the exponential function base e is just the exponential function base e. Really cool idea. Let's go ahead and prove this. So we're going to start with just saying let f of x equal e to the x. Kind of like what we did in the last definition back there. Well, then f prime of x is going to be the limit as h goes to 0 of e to the x plus h minus e to the x, and that's all over h. And here I'm going to just do a little manipulation. This is equal to the limit as h goes to 0 of e to the x times e to the h minus 1 over h. All I did was use the fact, the law of exponents from algebra 1, which is that e to the x plus h is the same thing as e to the x times e to the h. And then I factored out an e to the x out of the both terms in the numerator. Now, because e to the x does not involve h, let me just highlight that and show you what I'm talking about. Because this is not involving h, I can pull it outside of the limit. So I'll pull that factor outside the limit because it's not being affected as h goes to 0. So I'll just pull it out here. And we'll be left with a limit as h goes to 0 of e to the h minus 1 over h. And you look at that bad boy and you go, oh, but wait a second. E is the only base such that e to the h minus 1 over h as h goes to 0 will turn into 1 by definition. And so there you go. F prime of x is equal to e to the x, QED. Very nicely done. Now I can see somebody like watching this saying, wait, but how do we know that the limit as h goes to 0 of e to the h minus 1 over h is 1? How do we know that? And somebody else might say, well, because he said it's defined to be that way. It's a little bit of a hand-wavy statement. It's that we know there is a function, an exponential base. Even graphically, I know if you graph an exponential function, doesn't matter which exponential function is, all these exponential functions, they have some slope at x equals 0. You can adjust those exponential functions. It's supposed to be a b to the x, but it just didn't work out. You can adjust those bases to go to climb higher faster or to be more shallow. But we'd like to adjust it to the perfect value such that the slope at x equals 0 is 1. And we would call that, let's just call that c for now. So let's say that you don't know there's a number e that exists, okay? And I say, but wouldn't you agree that exponential functions all look like this? And you nod your head and you say, yes, I totally agree with that. And you say, wouldn't you also agree that as I raise this value of b, that function gets steeper and steeper? And you say, yeah, of course. And you say, great. Well, then if that slope right there is, let's say, a half, just for giggles, we should be able to gently adjust this b until we get to a value, we'll call it c, such that the slope here is 1. And people will probably say, yeah, okay, I could see that happening. Sure, why not? And you say, great. So you're saying that you're okay with me saying there is a exponential function. Let me zoom out a little bit. There's an exponential function whose derivative at x equals 0 is going to be 1. And you say, yes. I say, great. Because that's what this picture is. This picture is the derivative of an exponential function at time 0. It's 0 plus h, b to the 0th. But b to the 0th is 1, and there's no reason to write 0 plus h. So that's a derivative of an exponential function at x equals 0. And the person says, yes, it is. And I say, great. So our goal is to find that special base b so that that derivative, when x is 0, is 1. And your friend says, of course. Okay. So what we're going to do is, just for giggles, call that a letter. We're already using the letter B for base for so many other things. Let's use just a different letter. Your friend says, okay. And you say, how about the letter E? Now, this is probably where people get a little bit defensive and say, how do I know it's the letter E, though? That's fine. Let's say that you don't know it's the letter E. Call it the letter, I don't know, capital E, right? Even if you did it that way, everything still holds. You could say, okay, well then, if f of x is capital E to the x, then we have this, right? That's f prime of x, but we're not interested in f prime of x. We're interested in f prime at 0. So you go through and you replace all these. Go through all this, and you get to the same result. You just say, well, yay. So that means that f prime of 0 is equal to 1 for our function capital E to the x. I think the issue that a lot of people have is that I'm relating it to a lowercase e that means 2.71828, and so on and so forth. Or no, it's not. It's 2.718281828459045, and so on and so forth. So somebody is like, I just don't believe that that's the specific base. Well, you don't have to, honestly. You don't have to believe that. That's totally okay. But it turns out it is going to be that lowercase e in the long run. But you could do this whole proof without that assumption. You could say, well, just suppose it's a capital E. You could still do this whole entire proof. It would still work out. But I'm letting you know that it actually is going to be 2.718281828459045 and yada, yada, yada on forever, the number E. It will be that. It's just that I'm more like hand waving saying it's going to be that because I don't want to prove that part. In fact, let me try to convince you. I have b to the h minus 1 over h. I don't know what the base is. I know that h is tending to 0. Here's my slider for h right here. H tends to 0, right? We want this output to become 1. Wouldn't you agree? Yet, as I let h go to 0, you could see that b to the h minus 1 over h is not tending to 1. It's tending to something else. It's not tending to 0, though, but it's not tending to 1. So let's change up what h or what b is, what the base of our exponential is. And I think that I need to, oh yeah, step size is correct. So let's go ahead and do this. I'll just adjust this. Let's go to 2.5. Okay, so I'm just increasing this to 2.5. That's good enough. All right. Now I'll go ahead and decrease this. Oh, now this looks promising. It looks like it's heading to a value of 1. That's pretty good. When I say it looks, I mean this fraction value. It looks like it's heading to closer and closer to 1. But then it dips below it. Oh man, that sucks. Okay, so, but we see that if we chose a higher number, that it would approach a value, a higher value than it did before. So let's just rock it over to 3. Now I'm going to go ahead and decrease this and see if it decreases to 1. Well, no. No, I'm really close to an h of 0, and it's not at 1 yet. It's getting really close to 1. 1.099, but man, it's not really 1. So maybe I should lower that 3 a little bit. Let's go to 2.9. And I'll start lowering h, and you can see it's getting closer to 1. Great. But again, once I'm really close to 1, I'm within 1/1000th of it right there. It's still not close enough to 1. So this time I'm going to say, let me hold h constant here at 0.01. In fact, let me throw in a couple more zeros there. Okay, so h is really super small. Now I'm just going to find out what b is. So b 2.9, 2.8. Let's get this as close to 1 as possible. Okay. Oh, we just passed it, right? We just went below it. Let me raise it. 2.71. Between 2.718 and 2.719, maybe? Let me see. 2.718. Let's change it to 2.719. Oh, no. 2.719 is too large. 2.718. Let's increase that a little bit. 2, 8, 1, 8. 2.718, 28, 1, 8, 2, 8. And the reason why it's slightly greater than 1 is because I need more zeros here. Oh, now I broke Desmos. Okay. So 2.71828, 1828. For yeah, see, Desmos won't go anymore. But you can see it's around that number. That number is roughly E. So if I had put in here, I don't know if I can, but if I put in E, it will get very close to 1, incredibly close to 1. And unfortunately, Desmos won't allow me to put any more zeros in here because it causes undefined. But it's a good justification that you can see that base that affords that fraction to approach 1 as h gets really small is 2.718281828 yada yada yada, which is E. The long and the short of it is the derivative of e to the x is e to the x, and it makes it really nice when somebody asks, hey, find the derivative of this function, and you see part of your function has e to the x. So let's do a little bit of pre-work here before we find the full derivative of this. I'm going to write this as m of x is equal to, that denominator is x to the 1/3, but I want to write it in the numerator, so it's going to be x to the negative 1/3 plus e to the x plus x to the e plus e cubed. Now, notice that I try my best to do pre-work on a problem because I want everything to be a base x to a power if I can, if something is x to a power. So that's what I want to do. It just makes my life a little bit easier. This will imply the derivative of m with respect to x is equal to, you bring down that power, so it'll be a negative 1/3. And you'll have x to that same power minus 1. Remember that rule of bringing down the power. So if y is equal to x to the power, then y prime is p x to the p minus 1. That is only true if your base is x. The moment your base is not a variable, you cannot make that move. I'll say that till I'm blue in the face and people will still make the mistake. But plus the derivative of e to the x, we now know, is just e to the x. Plus a derivative of a base x to e. So my base is definitely x. I can totally do the bring the power down business. So e x to the e minus 1. I just brought down the power and then wrote that x with 1 less power. Sorry, I'm trying to get rid of the highlighter there. And then finally, plus e to the 3rd. Remember, e is not x. E is a constant. So a constant to the 3rd is still a constant. That derivative will be 0. And you would never write really plus 0. So you would just kind of keep that out of the picture. And that is the full derivative right there. Very fast. Very, very fast work. There's not much else that you can do. Once you've introduced exponentials, base e, there's not much else you could do with them. That's the best it gets. So
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.